So now that we have a general approach for figuring out if a matrix has an inverse, and if it does, finding that inverse, I want to take a few minutes and just go back to the 2 by 2 case, because it turns out that for a 2 by 2 matrix, there is a very handy formula that can be used. So in a sense, it's kind of a shortcut to the process of using Gauss-Jordan, and it's worthy of use, and not only that, it provides a quick efficient way to find the inverse of a 2 by 2 matrix. It also gives us a very easy check to see if a 2 by 2 matrix has an inverse, right? So how do we come up with this formula? Well, what we would have to do is use our process of Gauss-Jordan elimination, but not with a specific 2 by 2 matrix. It would have to be with a general 2 by 2 matrix. And let's see what would happen, right? So this is going to require us to do our Gauss-Jordan elimination not with specific numbers, but with like arbitrary constants, right? So let's see what it looks like. So let A be equal to A, B, C, D, right? And here, A, B, C, D can be any real number, right? So again, instead of picking specific numbers and forming a matrix and going through our process, let's see what that process looks like in a general way, all right? So to find A inverse, we know the process. We're going to augment this, so A, B, C, D, with the 2 by 2 identity, right? And so let's go. So the idea is to use our elimination process and turn the left-hand side into the 2 by 2 identity, and then we know what will happen here. We're going to have the inverse on this side. So first up, let's multiply the first row by 1 over A. So let's do 1 over A times row 1. Right? That will give us a 1 of a pivot here. This now makes it B over A. And then on this side, I have 1 over A, still a 0, and my second row stays the same. All right, so that's what it looks like by doing that operation. Why did we do 1 over A? Well, we want our pivot there to be 1, right? That's one of our requirements. Now, to eliminate the C, I have to do, maybe I can get it on this. Actually, let's not try to squeeze it there. Let's move to the next line. If I take negative C times row 1 and add that to row 2, right, that will eliminate this term, but then it's going to introduce a little bit of a mess in this term. But that's what we need to do in order to do this transformation, right? So now the first row stays the same, right? So we have that, and then 0. Then I have a 0 there, which is good. And then what's going to happen is I'm going to have D. Now this negative C is going to make this fraction negative CB over A. So minus CB over A. And then on this side, this will become negative C over A. Right? So negative C over A. And on this side, we still have a 1, right? So there we go. Now this D minus CB over A, let's actually write that as a fraction with a common denominator. So if I have D minus, and let me write it like this, BC over A, then if I want a common denominator, I can use A as my lowest common denominator, which means I have to multiply the first fraction by A, top and bottom. So by A there, by A there. So I'm going to write it like this, AD minus BC. So that's what I'm going to put. So I'm actually going to rewrite this matrix, right, this augmented matrix, before I actually do the next operation. So normally we would just move right into the next operation because we would have a specific number here. But since we have an expression, if I write this as a single fraction, it will allow me to identify what I need to multiply the second row by in order to get a 1 in that position, right? So no operation here, but just a little bit of algebra to rewrite this term right here. So we have 1, 0, b over a, and then write this instead. So it's AD minus BC all over a, right? And then the right hand side stays the same. Right, so again, this is where it takes a little bit of additional thought just to work through the process. But you can see we're not far away, right? We have to make this a 1, and then we have to eliminate this term, and then we will have the 2 by 2 identity, right? So in order to make this a 1, I need to multiply the second row by its reciprocal. And if you write the expression as a single fraction, then it's easy to identify what the reciprocal is. It's simply just flip this over. So I need to do a over AD minus BC times row 2. All right, so we know that the first row isn't going to change, so 1 over B minus A. Then we have 1 over A, 0. This is still a 0. Now when I multiply this fraction by its reciprocal, I'll get a 1 there. Now when I multiply this fraction by this fraction, the A in this numerator will reduce with this A in the denominator. So I'll be left with negative C over AD minus BC. So I'll have negative C over AD minus BC. And then over here, I'll just have A over AD minus BC. All right? So yes, the right-hand side is getting a little bit complicated, but one more expression and we should be good. So what are we going to do? To eliminate this term, I have to take negative b over a times row 2 and add it to row 1. So I need to do this. So negative b over a times row 2 plus r1, right? So negative b over a times row 2 added to row 1. And so we know we're going to get the identity there, so that's good. That's what we want. And then let me write the rest of the second row since that is now finished, right? So we have A, D minus, let's get this off. So AD minus BC. And then I have my A over AD minus BC. So let's see what's going to happen. I'm going to take this times this and then add it to the term above, right? So what will happen is, so let me write it like this. You're going to have 1 over A, and then it's going to be minus, and then I have BC on top. Well, actually it's going to be a plus BC because this is negative, this is negative, so plus BC, and then in the bottom I will have the A times this quantity, right? So A times AD minus BC, and then over here this will be just, what do we have? So negative B over A times A over AD minus BC. So the A's will cancel, and I'll have a negative B over AD minus BC. So the last term here, negative B over AD minus BC. All right, so certainly, these fractions we can say are simplified. This one isn't. Let's do like we did earlier. So let's take 1 over A plus BC over A times the quantity AD minus BC. So again, getting the common denominator is going to be A times the quantity AD minus BC. So that means I'll have to multiply this top by AD minus BC. So I'll have a AD minus BC, and then plus another BC over here. So the negative BC and the positive BC, those terms go away. And then I'm left with a common factor of A. So the A goes away. So now let's rewrite this. It's a little squished up there, but let me write it in all its glory right in the middle. Right? So here is the simplified form after doing our process, right? So in this entry right here, we have the D over AD minus BC. That's a D. There we go. So we have D over AD minus BC. And then this entry here is negative B over AD minus BC. And then a negative C over AD minus BC. And then finally A over AD minus BC. So let's write this down. So if we start out with this 2 by 2 matrix A, B, C, D, then its inverse is what I have here. Now look at it. See, the four denominators are exactly the same. So what I can actually do is use the reverse of our scalar multiplication and factor out 1 over AD minus BC. And I'm going to put that in front as my constant. So 1 over AD minus BC. And what I'm going to be left with is a D in this position, a negative B in this position, a negative C in this position, and then an A in that position. So essentially what I've done, just so that there's a very important pattern right here, in order to see that pattern, since the denominators are exactly the same, just factor that out and put it as my scalar. So I can express the inverse of this 2 by 2 matrix as this constant times this matrix, right? And look at the pattern. It looks like these two entries are swapped because the AD, so the entries on the main diagonal, they get swapped. There's the D that moves up there, and then there's the A that moves down here. And then the entries on the other diagonal, or the off diagonal, their signs change. That B turns into a negative B, and that C turns into a negative C. But the thing is, okay, so we have this formula, right? And we'll do a couple examples to show you how you use it. But the formula is also telling us something else important, because notice on this side, all we've done is just started with a 2 by 2 matrix with some numbers here, right? And so everything on this side is well defined. We have a 2 by 2 matrix, and we can put any quadruple of real numbers in these positions. Over here, this part looks the same, or looks okay as well. You take the negative of some numbers, you swap these two numbers. But look at this part of it now. This expression involves division. And with division, there is the possibility of dividing by 0. So the thing is, if, for instance, there ends up being a 0 in this denominator, then it means I can't actually do this operation because it will involve first taking the reciprocal of 0, which is not a real number. So what this tells me is that I now have an easy way to check to see if a 2 by 2 matrix has an inverse. How do I check it? I take AD minus BC, and if that number is not 0, then everything on the right hand side here is well defined. If the AD minus BC is 0, then now this is no longer defined, hence the inverse is no longer defined. So let's actually state that as a theorem. So we actually, and this was my intent, we prove this theorem simply by saying, okay, let's do our general process for a 2 by 2 matrix and see what happens, right? Just try it and see. Well, now we've seen what happens and we have a very useful formula for the 2 by 2, and we have an important check. So let's say this is our theorem. So let A equals A, B, C, D. Again, where there is no restriction on these numbers, right? It's just any old 2 by 2 matrix, right? And what I'll say this is if AD minus BC is not equal to 0, so that's the check we would do first. So if this number AD minus BC is not equal to 0, then I know the matrix has to have an inverse based on what I have here. So then A is invertible. So that would answer the first question. Is the matrix invertible? And so this is what we would do to test just for a 2 by 2, right? And if it passes that test, then we go ahead and use the rest of the formula to see that the inverse can be expressed like this. And its inverse, meaning the inverse of our original matrix, so its inverse is, and let's write it down, and it's the same formula right there. And it's a very easy formula with a nice pattern. So it's 1 over AD minus BC times this new matrix where it's D, negative B, negative C, A, right? And it's a really useful formula because what it does, the formula itself encapsulates everything that the process is supposed to. But what it does, it cuts out the need for the step-by-step elimination, right? But the downside is this only works for a 2 by 2. There is a formula for a 3 by 3. We could go ahead and do this same thing with a 3 by 3 and start out with a B, C, D, E, F, G, H, I, so 9 entries, and go through it this way. But that in itself would be a lot more algebra, and it would be a lot messier. The formula doesn't work out to be as nice and as neat as this formula for the 2 by 2, right? So this is, again, a special formula that applies to the 2 by 2 matrix, and it gives us everything we need as far as its inverse is concerned. So let's look at a couple examples here, right? So the first one asks this question: is A equals 1, negative 5, 3, 8 invertible? right? So let's answer, well, we'll ask that question, and we'll do a little explain, right? Love to explain. And then if so, find and verify A inverse, right? So basically 3 things we need to do, right? And let's start by answering the first question. So in this matrix, what do we have? We have our, here's A, so in fact, let me just kind of label them. So little a, B, C, D, right? So here's our check. So if I do 1 times 8 minus -5 times 3, right? And again, the easy way to remember the check is multiply the elements on the main diagonal. So that's 1 times 8. And then multiply the elements on the other diagonal and then subtract them, right? So again, do that AD minus BC. And in this case, we can see that it's definitely not going to be 0. Let's write down what the number is. So 8 plus 15, so that's 23. So because this is not equal to 0, the theorem tells me that A is invertible, right? So this implies A is invertible. And remember, a synonym for invertible is non-singular. Okay, so we have that. Then the other question is, well, where's our explanation? Well, that's our explanation right here, right? Explanation is because this AD minus BC is not equal to 0, right? So it's all wrapped up in here. We've answered the first question along with an explanation, and then it says find A inverse. Well, that's where we use our formula. So A inverse is 1 over the AD minus BC. So it's going to be 1 over 23 times, and then this is where we do that little shimmy and shake, right? So we're going to swap these two. So the D goes there, the A goes there, and then I change the sign of the elements on the other diagonal so that -5 becomes a +5, and that +3 becomes a -3, right? And there's absolutely nothing wrong with writing it like this. Many times, however, it might end up being more useful to go to distribute this scalar. So A inverse, oh, I forgot to write my inverse sign there. So A inverse is the matrix 8 over 23, 5 over 23, -3 over 23, and then 1 over 23, right? So we've answered that question, we've explained ourselves, we've found the inverse, so now to verify. How do we verify? Well, we go back to the definition of a matrix and its inverse. If I multiply these two, and in fact I've found the right inverse, I have to get the 2 by 2 identity. So here now let's do the verify. So to verify, take A, right, and multiply it by its inverse. So the 8 over 23, the 5 over 23, the -3 over 23, and then the 1 over 23. If this doesn't work, then it means I did something wrong, right? Let's see. So we have 8 over 23, so now doing a row times column multiplication. So 8 over 23, and then a plus 15 over 23, right? And then let's do the first row now, the second column. I have a 1 times 5 over 23, so that's 5 over 23. And then minus 5 over 23, everything's looking good so far because this is going to be equal to 1. This is equal to 0. Let's see if we get a 0 here. 3 times 8 over 23, that's 24 over 23, minus, there we go, minus 24 over 23. And then lastly, 15. So 15 over 23 plus 8 over 23. And there is our identity. So we have a 1 there, we have a 0 there, a 0, and a 1, right? So that's half of the verifying. What's the other half? Well, we have to switch the order because the definition requires that it shouldn't matter the order in which we do this, right? And I know this is, it's like, okay, a lot of arithmetic, but let's go through it again, right? So the verify part, 8 over 23, 5 over 23, negative 3 over 23, 1 over 23. Not only, again, is it good practice to really hit home what this inverse, the property that the matrix and its inverse has, but it's also, again, good practice with the matrix multiplication, right? So what do we have here? 8 over 23 plus 15 over 23. And then what do we have on this side? We have negative 40 over 23. And then a positive 40 over 23. And things are, again, looking good. Now let's see, second row, first column, negative 3 over 23 plus 3 over 23. And then finally, a positive 15 over 23. And then a positive 8 over 23. Let me write that more clearly. So over 23, and there is our identity. Because this is 23 over 23. This is clearly 0. Again, clearly 0. And again, 23 over 23. So now I can check off that we have verified that the inverse is in fact what we think it is, right? And again, it's just one level of assurance that you get. I know, like, you do something and okay, we proved it, and so, but does it really convince you? The proof should, right? For sure, that's what a proof does. But many times you want to see it in action, right? It seems like, it's like seeing it actually play out is better than seeing, the general argument in the proof. For me, it's the other way. I don't really need examples, right? I can see the truth in the proof. All right, so one more example, not necessarily of this process, but another type of question that can pop up with regards to the matrix and its inverse. So here's the second question. For what values, possibly, of k is 3 to k8 singular? Right? So again, I wanted to use that other word. Remember, singular means not invertible, right? So here's our matrix, and now the question is, I don't know what's in this position. It's like the k is just really a placeholder. So the question is really asking you, what number or numbers could I put in this position and then end up with a matrix that doesn't have an inverse, right? So again, a couple things as far as the terminology. The word singular is interchangeable with the phrase non-invertible. right? So if the matrix does not have an inverse, so how are we going to figure that out? Well, we have that check for a 2 by 2 matrix. So the next implication is in the 2 by 2 case, for the matrix to be non-invertible, that AD minus BC has to be equal to 0, right? So again, here's your A, B, C, D, and the theorem says if that AD minus BC is equal to 0, then I'll end up with a 0 in like this denominator, which can't work, right? So for the 2 by 2, the easy check is the 3 times 8 minus 2 times k. That has to be equal to 0. If that number is 0, then the matrix doesn't have an inverse. So solve this equation for k, because that's what the question is asking you. What values of k? What number, when I put it here, will guarantee that the matrix doesn't have an inverse? So solving gives 24 minus 2k is equal to 0, and it's easy to see that k has to be 12, right? So if you subtract your 24, divide by -2, right? So if I put a 12 there and try to find the inverse, good luck. It's not going to happen, right? But any other number other than 12, so if I put 11.9, or if I put 1,000, or if I put the square root of 2, any other real number that I put here will produce a matrix that has an inverse, all right? So the takeaways from this video is for this special case of the 2 by 2, not only do we have a relatively easy check. You're talking about multiplying two things and taking a difference. Oh, that's pretty easy. We have a nice check to see if the matrix has an inverse, and then we have that formula that tells us exactly what the inverse is when it exists, right? So think about it, make up some 2 by 2 matrices, try it out, and have fun. See you in the next video.